Coming to the first question. In figure 9.23, E is any point on the median AD of triangle ABC. Show that area of triangle ABE is equal to area of triangle ACE. Now moving on to solution. In triangle ABC, it is given that AD is a median from vertex A. That means a median from vertex A divides BC, that is base, in two equal halves. Therefore here we can say BD is equal to DC, which is equal to half times BC. He asks us to prove that area of triangle ABE is equal to area of triangle ACE. In order to prove that, let us draw a perpendicular AX perpendicular to BC. Now let us find the area of triangle ABD, which will be equal to half times base, that is here BD, into the height is AX here. Now let us similarly find the area of triangle ADC, which is equal to half times base here is CD into height here is nothing but AX, since ADC is an obtuse angle triangle. Now let us divide both the areas, then we get area of triangle ABD divided by area of triangle ADC is equal to half times BD into AX by half times CD into AX. Here half into AX is common in numerator and denominator, that will be cancelled, which is equal to BD by CD. But we know that BD and DC are equal since AD is a median. Therefore that value will be equal to 1. Finally we get area of triangle ABD is equal to area of triangle ADC. From this statement we can say that median in a triangle divides the area into two equal halves. Now let it be as equation number 1. Now in triangle BEC, as BD is equal to DC, we can say ED is the median. In the above, we proved that median divides the triangle area into equal halves. We can say here area of triangle BED is equal to area of triangle EDC. Now area of triangle BED can be written as area of whole triangle ABD minus area of triangle ABE. That is, area of triangle BED can be written as area of triangle ABD minus area of triangle AEB, which is equal to, here area of triangle EDC can be written as area of triangle ADC minus area of triangle AEC. That is, area of triangle EDC can be written as area of triangle ADC minus area of triangle AEC. Now let us rearrange the terms, then we get area of ABD triangle minus area of triangle ADC is equal to area of triangle AEB minus area of triangle AEC. Since we have sent the ADC to right hand side and we took minus area of AEB to right hand side, which implies as area of ABD is equal to area of ADC, the difference in between them will be equal to 0. We got area of triangle ABD is equal to area of triangle ADC in the first equation. Therefore 0 is equal to area of AEB minus area of AEC, which implies this 0 we got it from equation number 1. So let it be presented. That implies area of AEB is equal to area of triangle AEC. This can be written as area of ABE is equal to area of ACE. This is what the required proof for us, that is hence proved. Moving on to second question. In triangle ABC, E is midpoint of median AD. Show that area of BED is equal to 1/4 of area of ABC. Now moving on to the solution. Let us consider triangle ABC with the median AD in it and consider E as midpoint and join BE. Then what we need to show is here area of BED is equal to 1/4 of area of ABC. As we know that E is midpoint of AD, AE is equal to ED. Here in triangle ABC, it is given that AD is median. Therefore, BD will be equal to DC. We know that in triangle, a median always divides area into two equal halves. Therefore, here area of triangle ABD will be equal to half times area of triangle ABC. Now again, if we consider from figure in triangle ABD, as E is the midpoint of AD, AE will be equal to ED and therefore BE will be the median. Therefore, in triangle ABD, the median divides area of triangle ABD into two equal halves. Therefore, area of triangle BED will be half times the area of whole triangle, that is triangle ABD. But from the above we have that area of triangle ABD is nothing but half times area of triangle ABC. So let us substitute that, then we get half times area of ABD can be replaced by half times area of ABC, which implies area of triangle BED is nothing but half times half area of triangle ABC, which implies area of triangle BED is equal to 1/4 times area of ABC triangle. This is what our required proof. Coming to the third question. Show that the diagonals of the parallelogram divide it into four triangles of equal area. Now moving on to the solution. Let us consider a parallelogram ABCD whose diagonals are AC and BD respectively, which are intersecting at point E. Now we know that if ABCD is a parallelogram with AC and BD as diagonals, let us note some of the properties of parallelogram. We know that in parallelogram opposite sides are parallel and are equal, and also in parallelogram diagonals bisect each other. Therefore here AC is bisecting BD and mutually BD also bisects AC. Therefore here we can say that AE will be equal to EC since BD bisecting AC, and ED will be equal to EB since AC bisects the diagonal BD. Now let us consider triangle ADB. Here ED is equal to EB. Therefore we can say that AE is the median of the triangle ADB. As AE is the median, we can say in triangle ABD it divides the triangle AEB and triangle AED in the same area, same ratio of area. That is, area of triangle AED is equal to area of triangle AEB. Similarly, if we consider triangle BDC, in triangle BDC, ED is equal to EB. Therefore, CE becomes the median, and this median divides the area in the equal ratio. That is, area of triangle CEB will be equal to area of triangle EDC. Let it be as equation number 1 and let it be as equation number 2. Now, let us consider triangle ABC. In triangle ABC, AE is equal to EC. Therefore, we can say that EB is the median. When EB is the median, then it divides the area of triangle ABC into equal halves. That is, area of triangle AEB is equal to area of triangle EBC. Let it be as equation number 3. Now, from equation 1, 2 and 3, as area of triangle AED is equal to area of triangle AEB, and this AEB triangle area is equal to triangle ABC, and this triangle EBC area is equal to area of triangle CED, that is from 2. We can say that area of triangle AED is equal to area of triangle AEB is equal to area of triangle EBC is equal to area of triangle EDC. As this is equally divided into the 4 equal halves, that will be equal to 1/4 of total area of parallelogram, that is ABCD. Therefore, finally we can say that diagonals of the parallelogram divide the parallelogram into the 4 triangles of equal area. Moving on to the 4th question. In figure 9.24, ABC and ABD are 2 triangles on the same base AB. If line segment CD is bisected by AB at O, show that area of triangle ABC is equal to area of triangle ABD. Now moving on to the solution. He has given that CD is bisected by AB at O. Therefore, we can say that OC is equal to OD. Now, let us consider in triangle ACD, as OC is equal to OD, we can say that AO is median. Therefore, we know that in triangle, a median divides the triangle in the 2 equal halves, that is of same area. Therefore, here both the areas will be equal, that is area of triangle AOC is equal to area of triangle AOD. Let it be as equation number 1. Now similarly, if we consider in triangle BCD, OC is equal to OD, therefore we can say that BO is the median. We know that in a triangle, median divides the area of triangle into 2 equal halves. Therefore we can say that here area of triangle BOC is equal to area of triangle BOD. Let it be as equation number 2. Now let us add both the equations, that is equation 1 plus 2, which implies area of triangle AOC plus area of triangle BOC is equal to area of triangle AOD plus area of triangle BOD, which implies here the area of triangle AOC, this is the shaded region, and area of triangle BOC, which is the other shaded region, is equal to total area covered under ABC. Therefore, area of triangle ABC is equal to area of triangle AOD, that is the dotted portion represented, and area of triangle BOD, let us represent with the dotted portion. Then sum of those areas is equal to the complete area covered by area of triangle ABD. Therefore, finally we got that area of triangle ABC is equal to area of triangle ABD. This is what our required proof. Moving on to fifth question. D, E and F are respectively the midpoints of sides BC, CA and AB of triangle ABC. Show that BDEF is a parallelogram. Second one, area of triangle DEF is equal to 1/4 of area of ABC, and area of parallelogram BDEF is equal to half times area of ABC triangle. Now moving on to the solution. Let us consider a triangle with DE, E, F or the midpoints of sides BC, CA and AB. Now by joining them to the opposite vertices, then we get them as medians, and point of intersection of medians is known as centroid. So this is the figure in which AB, BC, CA are sides of triangle ABC, and E is midpoint of AC, D is midpoint of BC, and F is the midpoint of AB. Now initially we are required to prove that BDEF is a parallelogram. Area of triangle DEF is equal to 1/4 of area of triangle ABC, and area of BDF is equal to half times area of ABC. Let us join DE and also EF. Now if we consider in triangle ABC as D is midpoint of BC, we can say BD is equal to DC, which is equal to half times BC. And he also says that F is midpoint of AB and E is midpoint of AC. Then from the midpoint theorem we know that if F is midpoint of AB and E is midpoint of AC, then EF will be equal to half times BC, and also EF will be parallel to BC. Therefore, which implies EF is equal to half times BC can also be written as BD, and also EF parallel to BC. As EF is parallel to BC, it will be obviously parallel to the half of BC, that is nothing but BD. Let it be as equation number 1. Now let us consider again the triangle ABC. In triangle ABC, now consider that F is midpoint of AB. Then we get AF is equal to FB, which is nothing but half times AB, and as we know that here E is midpoint of AC and also D is midpoint of BC. From midpoint theorem, DE will be half of AB and also DE will be parallel to AB. That implies DE is equal to half times AB can be replaced by BF or FB, and DE parallel to AB is implies DE is also parallel to FB. Now in figure BDEF we got that, let be as equation number 2, we got that from equation 1 and 2 opposite sides are equal and are parallel. Therefore the quadrilateral BDEF is a parallelogram. This is what our first proof required. Here, in the second proof, we are required to prove that area of triangle DEF is equal to 1/4 of area of triangle ABC. So now let us join the triangle DEF. Now in the figure, if we consider here the parallelograms BDEF is similar to parallelogram DFEC. Therefore here, as area of DEF is common in between them, we can say in parallelogram BDEF, area of FBD triangle is equal to area of triangle DEF, and also area of triangle DEF is equal to area of triangle CDE. And if we consider the parallelogram BDEF, it is similar to parallelogram DFAE. Therefore we can say that area of triangle FED or DEF is equal to area of triangle AFE. Now by all these equations we can say that area of triangle AFE is equal to area of triangle FBD is equal to area of triangle DEF is equal to area of triangle CDE. By adding all this, we get the whole area of triangle ABC. Therefore we can say that area of triangle ABC is equal to area of triangle AFE plus FBD plus area of triangle DEF and CED. But all these areas are equal, therefore we can write 4 times the area of DEF, which implies area of DEF is equal to 1/4 times area of ABC. This is for the second proof. And he asked us to find the area of parallelogram BDEF, that is area of parallelogram BDEF is equal to area of triangle BDF and area of triangle FDE, that is equal to, we can replace it by area of triangle DEF, that is from equation number 1 in Roman, plus area of FDE can also be replaced by area of DEF, that is equal to 2 times area of DEF, which is equal to 2 times area of DEF. We got it as 1/4 of area of ABC, that is second proof, which is equal to half times area of ABC triangle. Therefore finally we got that area of parallelogram BDEF is equal to half times area of triangle ABC. This is what our third proof. Moving on to sixth question. In figure 9.25, diagonals AC and BD of quadrilateral ABCD intersect at O such that OB is equal to OD. If AB is equal to CD, show that area of triangle DOC is equal to area of triangle AOB, area of triangle DCB is equal to area of triangle ACB, and DA parallel to CB, or else ABCD is a parallelogram. Now moving on to the solution. Here he has given a quadrilateral ABCD in which AB is equal to CD, and also he says that OB is equal to OD. Now let us consider in triangle DBC, OB is equal to OD. Therefore, we can say that CO is the median. As CO is a median, we can say that it divides the area of triangle DCB into two equal halves, that is, area of triangle DOC is equal to area of triangle COB. And again, if we consider in triangle DAB, OB is equal to OD, AO is the median. Therefore, we know that in triangle area is divided by the median into two equal halves. We can say here area of AOD is equal to area of AOB. Now let this be as equation number 1 and this be as equation number 2. So therefore by adding both equations we get area of triangle DOC plus area of triangle AOD is equal to area of triangle COB plus area of triangle AOB. That implies area of triangle DOC plus AOD is nothing but area of triangle DAC, which is equal to area of triangle COB plus AOB is nothing but area of triangle ABC here. Here we got area of triangle DAC is equal to area of triangle ABC. Now we shall draw DX perpendicular to AC and BY which is perpendicular to AC. Therefore, now we can say area of triangle DAC will be half times base here is nothing but AC into height here is DX, which is equal to half times base in triangle ABC is nothing but AC into height here is BY. That implies DX is equal to AY. Now let us consider both the triangles, that is triangle DXC and triangle BYA. In these both triangles, angle DXC is equal to angle BYA, which is equal to 90 degrees, and hypotenuse DC is equal to hypotenuse AB in both the right angle triangles, and also we got DX is equal to AY. Therefore, we can say that triangle DXC is congruent to triangle BYA by the right angle hypotenuse side property of congruency. We know that when two triangles are congruent, then their corresponding angles and corresponding sides will be equal. Therefore, here we can equate angle DCX is equal to angle YAB. Here, therefore, they become the alternate interior angles for the lines AB and CD with the AC as transversal. Therefore, as here the alternate interior angles are equal, we can say that DC is parallel to AB, and initially it is given that DC is equal to AB. Therefore, now in quadrilateral ABCD, opposite sides are parallel and are equal. Therefore, we can say that quadrilateral in which one of the opposite sides is parallel and or equal is a parallelogram. Therefore, here we can say that given ABCD is a parallelogram. Now, we know that in a parallelogram, diagonals bisect each other perpendicularly. We know that in a parallelogram, diagonals bisect each other. We can say O divides AC in the 1:1 ratio. Therefore, here OA will be equal to OC. Now, let us consider in triangle DAC, OC is equal to OA. Therefore, here area of triangle DOC will be equal to area of triangle DOA. And also in triangle ABC, as OC is equal to OA, area of triangle BOC will be equal to area of triangle AOB. But we know that area of triangle DOC is equal to area of triangle BOC. Therefore, we can say that area of triangle DOC will be equal to area of triangle AOB. This is what our first proof required. Since we get that area of triangle DOC is equal to area of triangle BOC. Now let us name these equations as equation number 3 and this as equation number 4. Here let us add the area of triangle OCB on both sides, which is equal to area of triangle AOB plus area of triangle OCB. That implies area of triangle DOC plus OCB is nothing but area of triangle DCB, which is equal to area of triangle AOB plus area of triangle OCB is nothing but area of triangle ABC. Therefore, finally we can say that area of triangle DBC is equal to area of triangle ABC. This is what the required proof for us. Moving on to 7th question. D and E are the points on sides AB and AC respectively of triangle ABC such that area of DBC is equal to area of EBC. Prove that DE is parallel to BC. Now moving on to solution. Let us consider a triangle ABC as shown in figure and let DB point on AB and EB point on AC. Now let us join DE and also join B to E and also D to C. So what we have done here is we have joined DE, BE and DC. Here he has given that area of triangle DBC is equal to area of triangle EBC. Now let us consider in triangle DBC and triangle EBC, draw a perpendicular to base BC, that is DX, and also draw another perpendicular EY perpendicular to base BC. So what we have done here is draw DX perpendicular to BC and also EY perpendicular to BC. Now we get area of triangle DBC is equal to half times base, that is BC, into height is DX, and area of triangle EBC will be equal to half times BC times height here is EY. But here we know that area of triangle DBC is equal to area of triangle EBC. Half times BC times DX is equal to half times BC times EY. That implies DX is equal to EY. As the perpendiculars between the two lines are equal, we can say that DE is parallel to BC. This is what the required proof for us. Coming to the 8th question. XY is a line parallel to side BC of triangle ABC. If BE is parallel to AC and CF is parallel to AB, meet XY at E and F respectively. Show that area of triangle ABE is equal to area of triangle ACF. Now moving on to the solution. Let us consider a triangle ABC as shown in figure. In this, he says that there is a line XY which is parallel to BC, and he says BE is drawn such that it is parallel to AC. So let us join here BE with X. Now he also says that there is another line CF such that it intersects YF XY at F. Now, initially it is given that XY is parallel to BC, and now let us consider quadrilateral BEYC. In this, we know that XY is parallel to BC, which implies EY is also parallel to BC. And also, he has given that AC is parallel to BE, which is drawn by us. That implies CY will be parallel to EB. Therefore, here in the quadrilateral BCYE, two opposite pair of lines are parallel. Therefore, we can say that here the quadrilateral BCYE is a parallelogram. Therefore, in the parallelogram, opposite sides will be of equal length. Here we can say BE is equal to CY, and also BC is equal to EY. Let us also join AE and AF. Here we need to prove that area of triangle ABE is equal to area of triangle ACF. Now let us consider the quadrilateral BCFX. In quadrilateral BCFX, XY is parallel to BC, which implies XF will be also parallel to BC, and as CF is parallel to AB, we can say CF is also parallel to BX. Therefore, in the quadrilateral BCFX, we have opposite pair of lines as parallel. Therefore, we can say that here BCFX is a parallelogram. In a parallelogram, we know that opposite sides are parallel and are equal. Therefore, here we can equate BX is equal to CF and BC is equal to XF. Here in the first step, we got that BC is equal to EY, and in the second step, we got BC is equal to XF. Therefore, here we can equate EY is equal to XF, which implies EY is nothing but EX plus XY, that is equal to XF is nothing but XY plus YF, that implies EX is equal to FY. Now we got EX is equal to FY. Let us draw BP perpendicular to EX and CQ perpendicular to YF. Draw PB perpendicular to EX and CQ perpendicular to FY. We know that if there are two parallel lines and consider 4 points on them like PB and QC, we know that perpendicular distance between two parallel lines is always constant throughout the continuation of the parallel lines. Therefore, we can say that here PB is equal to CQ. Now, let us find the area of triangle BEX, which is equal to half times base is nothing but EX times height is nothing but BP. And here area of triangle CYF is equal to half times base here is YF times height here is CQ. We know that. Let us find the ratio of these two triangles. Then we get area of BEX by area of CYF is equal to ratio of half times EX by BP and divided by half times YF into CQ, which is equal to, as EX is equal to YF, we get the ratio of 1, and BP by CQ will be also 1 since BP is equal to CQ. Therefore, whole ratio will be equal to 1. Therefore, we can finally say area of triangle BEX is equal to area of triangle CYF. Let it be as equation number 1 in Roman. Here, in the since first condition we got EX is equal to YF, we can say triangle AEX and AYF have common bases. As some AZ will be the perpendicular height for both the triangles, we can say the perpendicular height for both the triangles is equal and we have here common base. Therefore, areas of those triangles also will be equal, that is area of triangle AXC is equal to area of triangle AYF. Let it be as equation number 2 in Roman. Now by adding 1 and 2 we get area of triangle BEX plus area of triangle AXC is equal to area of triangle CYF plus area of triangle AYF, which implies area of triangle BEX plus AXC is nothing but area of triangle ABE or AEB, which is equal to area of triangle CYF plus AYF is nothing but area of triangle ACF. So this is what the required proof for us, and it is hence proved. Moving on to 9th question. Side AB of parallelogram ABCD is produced to any point P. A line through A and parallel to CP meets CB produced at Q, and then parallelogram PBQR is completed. Show that area of parallelogram ABCD is equal to area of parallelogram PBQR. Now moving to the solution. Let us join AC and PQ according to the given hint. Then we get area of triangle ABC is equal to half the area of parallelogram ABCD. Since the parallelogram and triangle ABC lie about the common base AB and in between the two common parallels, that is AB and CD. And next, if we consider in parallelogram PBQR, area of triangle BPQ will be half times area of parallelogram BPQR, since they lie in between the common parallels PB and QR and about the common base BP. Let them be as equation number 1 and equation number 2. Now here triangle ACQ and triangle AQP lie about the common base AQ and in between the common parallels AQ and CP. Therefore, area of two triangles lying in between the common parallels and a common base will be equal. Therefore, here we can equate area of triangle ACQ is equal to area of triangle AQP. From this, let us separate the area of triangle AQB. Then we get area of triangle ACQ minus area of triangle AQB is equal to area of triangle AQP minus area of triangle AQB, which implies area of triangle ACQ minus area of triangle ABQ or AQB is equal to area of triangle ABC or ACB, which is equal to area of triangle AQB minus ABQ is BPQ. But from 1 and 2 we have area of triangle ABC is nothing but half times area of parallelogram ABCD, and area of BBQ is half times area of parallelogram BPQR. That implies area of parallelogram ABCD is equal to area of parallelogram BPQR. This is what the required proof for us, and it is hence proved. Moving on to 10th question. Diagonals AC and BD of trapezium ABCD with AB parallel to DC intersect each other at O. Prove that area of triangle AOD is equal to area of triangle BOC. Now moving to the solution. Let us consider a trapezium ABCD in which AB is parallel to DC, and he says that diagonals AC and BD bisect each other at O. We need to prove that area of triangle AOD is equal to area of triangle BOC. Now, as he has given that AB is parallel to DC, let us consider the two triangles, that is triangles ABC and triangle ADB. These both triangles lie about the common base AB and in between two common parallels, that is AB and CD. Therefore, we can say that area of triangle ABC will be equal to area of triangle ADB. Let us subtract area of triangle AOB from these both triangles. That is area of triangle ABC minus area of triangle AOB is equal to area of triangle ADB minus area of triangle AOB. That implies area of triangle ABC minus area of triangle AOB is nothing but area of triangle BOC, which is equal to area of triangle ADB minus area of triangle AOB is nothing but area of triangle AOD. This is what the required proof for us. Moving on to question number 11. In figure 9.27, ABCDE is a pentagon. A line through B parallel to AC meets DC produced at F. Show that area of triangle ACB is equal to area of triangle ACF and area of parallelogram AEDF is equal to area of pentagon ABCDE. Now moving on to the solution. Here he has given that ABCDE is a pentagon, that is ABCDE is a pentagon. A line through B is drawn parallel to AC and DC is produced at F. So the above information as shown in figure. Now from the figure, if we consider, here we can say that ACBF forms a parallelogram. So now as AC is parallel to BF, if we consider the two triangles, that is triangle ACB and triangle ACF, they both lie about the common base AC and in between two common parallels AC and BF. Therefore, we can say that area of triangles lying in between the common parallels and having the common base will be equal. Therefore, here we can say area of triangle ACB is equal to area of triangle ACF. Now, In order to get the area of AEDF, that is AEDF, we need to add area of ACF with area of AEDC. Therefore, let us add AEDC on both sides. Then we get area of triangle ACB plus area of quadrilateral AEDC is equal to area of triangle ACF plus area of quadrilateral AEDC. That implies area of triangle ACB plus area of quadrilateral AEDC gives area of pentagon ABCDE, which is equal to area of triangle ACF and area of AEDC quadrilateral gives area of AEDF quadrilateral. This is what the second proof we require to prove, and initially we proved the first proof. Therefore, this is what the required proofs for us, and it is hence proved. Moving to the 13th question. ABCD is a trapezium with AB parallel to DC and line parallel to AC intersects AB at X and BC at Y. Prove that area of ADX is equal to area of ACY. Now moving to the solution. Let us consider ABCD is a trapezium, that is as shown in figure. Let us consider AC as diagonal. Here he says that a line parallel to AC intersects AB at X and BC at Y. Therefore, let us consider a line parallel to AC intersecting AB at X and BC at Y. Then he asks us to prove that area of triangle ADX is equal to area of triangle ACY, that is ACY. Let us join this. Now, in order to do the problem, let us join CX. Now, if we consider the both triangles, that is triangle ADX and triangle ACX, that is ADX is over here and ACX is over here, they lie in between two common parallels, that is AX and CD, and also they have the length of the bases as equal. Therefore, we can say that area of two triangles lying in between the two common parallels and having the common base length will be having equal areas. Therefore, here we can say that area of triangle ADX is equal to area of ACX triangle. Let it be as equation number 1. Now, let us consider the two triangles ACX and AXY. That is ACX is over here and AXY is over here. Now, these two triangles have common base, that is AX. Here, triangles ACX and in triangle ACY, that is ACX is over here and triangle ACY is over here. In these triangles, they lie about the common base, that is AC, and they also lie in between the common parallels, that is AC and XY. Therefore, we know that area of triangles lying in between the common parallels and with common base will have equal areas. We can equate area of triangle ACX is equal to area of triangle ACY. Let it be as equation number 2. Then from equation 1 and 2 we can say that area of triangle ADX is equal to area of triangle ACY. Now moving on to the 14th question. In figure 9.28, AB parallel to BQ parallel to CR, prove that area of AQC is equal to area of PBR. Now moving to the solution. Let us consider initially the triangles ABQ and triangle PBQ. These both triangles lie about the common base BQ and in between the common parallels AP and BQ. Therefore, we know that if two triangles lie in between the common parallels and having the same base, their areas will be equal. Therefore, area of triangle ABQ will be equal to area of triangle PBQ. Similarly, let us consider the triangles BQC and BQR. These both triangles lie about common base BQ and also lie between two parallels, that is common BQ and CR. Therefore, we know that if two triangles are lying in between the common parallels and with the common base, their areas will be equal. Therefore, area of BQC will be equal to area of BQR. Let this be as equation number 2 and above one be as equation number 1. Now, by adding 1 and 2, we get area of ABQ plus area of BQC is equal to area of PBQ triangle plus area of BQR triangle, which implies area of ABQ plus BQC is AQC area, which is equal to area of PBQ plus area of QBR is equal to area of PBR. Therefore, this is what the required proof for us. Hence proof. Now, moving on to the 15th question. Diagonals AC and BD of quadrilateral ABCD intersect at O in such a way that area of AOD is equal to area of BOC triangle. Prove that ABCD is a trapezium. Now moving to the solution. Let us consider a quadrilateral ABCD. Here in this quadrilateral, let diagonals BD and AC intersect at common point O. Here he has given that area of triangle AOD is equal to area of triangle BOC. That implies, let us add area of triangle AOB on both sides. Then we get area of triangle AOD plus area of triangle AOB is equal to area of triangle BOC plus area of triangle AOB. That implies area of triangle AOD plus area of triangle AOB is nothing but area of triangle ADB, and area of triangle BOC plus area of triangle AOB is nothing but area of triangle ABC. Now, if we consider triangles, that is triangle ADB and triangle ABC lie about the common base AB, and we know that areas of triangles lying with the common base are equal if they lie in between the common parallels. Therefore, here if we consider the figure, triangle ADB and triangle ABC lie about the common base AB, and in between the lines AB and CD. As their areas are equal, we can say that AB will be parallel to CD. Therefore, in a quadrilateral, if one of the set of lines is parallel, then it is a trapezium. Therefore, ABCD is a trapezium here. Moving on to 16th question. In figure 9.29, area of triangle DRC is equal to area of triangle DPC and area of BDP is equal to area of triangle ARC. Show that both the quadrilaterals ABCD and DCPR are trapeziums. Now moving on to the solution. Let us consider the given figure, and in that he has given that initial condition area of triangle DRC is equal to area of triangle DPC. So let us consider in the figure, that is area of triangle DRC and area of triangle DPC are given equal. They lie about the common base DC. Here, as the areas of triangles which are lying between the lines CD and PR are equal and they lie about the common base CD, and it is possible for the triangles lying between the two sides or two lines to be equal if they lie about the common base and they lie in between the two common parallels. Therefore, here from that statement we can say that DC is parallel to RP here. Therefore, in quadrilateral DCPR, one of the set of lines is parallel. Therefore, we can say that quadrilateral with one of the set of lines is parallel is nothing but trapezium. Therefore, here DCPR is a trapezium. Now, let us consider the second condition given, that is area of BDP is equal to area of ARC. That implies here let us subtract area of BDP from area of DCP or DPC, that is equal to area of ARC minus area of DCP. That implies area of BDP minus DCP is nothing but BDC, that is equal to area of ARC minus area of DCP. DCP is DRC, that is from initial given condition. Now here area of triangle BDC is equal to area of triangle ARC minus area of triangle DRC is nothing but area of triangle ADC. Now here if we consider BDC and ADC, they lie about common base CD and they lie in between the two lines, that is AB and CD. If the areas of two triangles lying about the common base are equal unless and until if the two lines in between which they lie must be parallel. Therefore, here AB must be parallel to CD. Therefore, in quadrilateral ABCD, one of the pair of opposite sides are parallel. Therefore, the quadrilateral in which one of the pair of opposite sides are parallel is a trapezium. Here, ABCD is a trapezium. In the first case, we proved that DCPR is a trapezium, and in the second case, we proved that ABCD is a trapezium. This is what the required proof for us, and it is hence proved.